For example 3, you're told to let S equal the numbers 1, 2, and 3. They're associated with events that are occurring in an experiment. List all possible events of this experiment, which means basically you want to list all possible subsets of this, so they could contain just one element, multiple elements, so you want to list all of them. You want to tell me how many subsets contain the number 3 and how many subsets of S contain either the number 2 or the number 3. Okay, so again, all events for this experiment are any and all subsets of the sample space. So the empty set is always considered to be a subset. I can have a set of nothing from S, so it is possible. The set of 1, the set of 2, the set of 3, those individuals would be subsets. I have the set of 1 and 2, the set of 2 and 3, the set of 1 and 3, those would be subsets that contain 2 elements. And of course, I only have one possibility for a subset that contains all 3, and that's basically S itself. So any sample space could be a subset of itself. So now when I go and answer the questions for B, having these listed does make it easier for me to answer the question, because it's asked how many subsets of S contain the number 3. Well, I can see there I had 8 subsets, 4 of them contain the number 3. So I could say 4 of them, in this case 4 of them, but eventually when I start talking about probabilities, I would say, okay, well, half of them do. 4 out of 8, so 50% of them would contain the number 3. How many subsets of S contain either the number 2 or the number 3? Well, again, I look at that, and we always assume that if we're given an either or when we talk about probabilities and such, that it's always considered to be inclusive, which means you include both of them. If there's both is part of that. So this doesn't say either 2 or 3, but not both. It's saying, okay, either 2 or 3, and both would be considered part of that as well. And as you can see, 6 of them have either the number 2 or the number 3 contained in it. Example 4. As part of a quality control procedure, an inspector at Bristol Farms randomly selects 10 eggs from each consignment of eggs he receives and records the number of broken eggs. What is an appropriate sample space for this experiment? Describe the event E, that at most 3 eggs are broken, and describe the event F, that at least 5 eggs are broken. So basically, what you want to use for these is, when you're looking for an appropriate sample space, you're looking for, well, okay, if we're going to let the numbers in this sample space, it should stand for the number of eggs that are broken. So you have to think, well, how many eggs could be broken? So you want to think of that as you're writing out, okay, well, what list of numbers would describe the number of eggs that could possibly be broken? And then E and F being subsets of that, how would you write those out to be, based on their description? How would you what elements from S would fall into that? So, okay, so what is an appropriate sample space for this experiment? So basically, since I have 10 eggs, and what we're looking at are the number of eggs that are broken, then basically my sample space can range from 0 to 10. And so it's going to be all integers from 0 to 10. Because it makes sense. I mean, I could have 0 eggs broken, 1 egg, 2 eggs, 3 eggs, so forth and so on, up to 10 eggs broken. I can't have less than 0 eggs broken, because I'd have to have negative eggs, which I don't makes any sense. And I certainly can't have 11 broken eggs out of 10. Okay, or any number bigger than 10, because it wouldn't make any sense. So this would be the sample space. Now, as far as E goes, describe the event E that at most 3 eggs are broken. Well, at most means at most 3. So any number leading up to 3 or less would be falling into the set. So E would be described by the subset 0, 1, 2, and 3. And at least 5 eggs for F, that would mean 5 or more. So F would be described as 5, 6, 7, 8, 9, and 10. we're going to make use of these kind of ideas about thinking about the possible events when we start getting into more probability things and coming up with what we call a probability distribution, which in many cases does make finding probabilities, especially for more complicated events, a lot easier.